Okay. All right. Oops, I have to now agree to it here. Okay. Hello, everyone. It's great to be here. As was pointed out, this is actually, I've never given this talk before. I prepared this talk just for this audience because I got the invitation and I couldn't resist kind of giving my own personal take on my own efforts with middling success, I would say, but with some success to, I guess, jam use of the FFT into deep learning. So I'll talk about what I mean by that. But I want to start off by saying, sort of, why do I care so much, I think, about the FFT, and why do I like it so much? So this actually goes back to when I was a grad student. I'm maybe a little bit. Actually, sorry. My outline should happen next. So, okay, some background about why do I care so much? So when I was a grad student, I took this course called the Fourier transform and its applications by Brad Osgood at Stanford. And this was a sort of I was in CS, right? I'm not doing a whole lot of statistical signal processing. And this course along with convex optimization taught by Stephen Boyd, so it really changed my outlook on how I approach problems. This was a fantastic course. It's also all for free online. So for all the grad students or maybe even faculty that haven't seen this course before and are not familiar with it, I can't recommend it enough. And just to give a sense, I was thinking back to it, and I, putting the slide together, I just remember how it was taught and how it was written. He has this great quote when he's talking about the fact that the Fourier transform of the Gaussian is a Gaussian, and he has this great statement saying, he's using this integral fact, using the Gaussian integral fact, and says that Lord Kelvin mentioned that this was, a true mathematician is someone that understands this equation the same way you and I, or the normal person, would understand 2 + 2 = 4. And then Brad sort of mentioned this was such a ridiculous statement, and I loved the sort of the candor and keenness with which he approached this topic for someone outside the area, right? And so ever since then, I've been trying to figure out a way to bring these topics, I would say, into my normal area of study, which is machine learning and AI. So now, actually, I guess going back, my slides are a bit out of order here. I'm going to talk by talking a little bit about convolutional networks, because convolutions are sort of at the center of the FFT, right? This is sort of the central theorem of FFTs relates to convolutions. And what we do in machine learning these days deals a whole lot with convolutions. So I'm going to give a bit of background on convolutional neural networks, then talk about what the FFT can do for ConvNets, which is surprisingly not that much so far, but hopefully more going forward. I really think there's a really undeveloped area here that more people need to know about, because there's only so much that one group can do. And end with some final thoughts. So, okay, we'll start talking about convolutional networks to start off with. So before I jump in here, let me just say this fact, which maybe is known to everyone here. But convolutional networks, which I'll talk about what they are in a second, have been the single most important network structure that has led to the current revolution in machine learning, right? So full stop. There's really no question about this, I think. So if you look at sort of what are the networks that have had a big effect on, or the applications that have had a big effect on blowing up the popularity of machine learning, the fact that we get invited to give talks at mathematics conferences now and things like this, they're convolutional networks, right? So ResNets, of course AlexNet. They're also great, by the way, if you want to really get cited heavily. You should write about convolutional networks. These are less than 10 years old now, and they all, well, not quite that one yet. They all have more than 100,000 citations. I believe ResNets are the most highly cited paper ever, or something like this now, at least within the last several years or something. It's a little bit absurd. But yeah, so this is 7 years old, on its way to 1,300,000 citations. 130,000 citations. But it's not just these sort of networks too. So if you think about the applications, like what's been accomplished with machine learning models recently, you probably think about things like the ImageNet classification challenge, or maybe Atari game playing, or AlphaGo. And these are all convolutional networks. This may be changing now. So some of the new networks, I know transformers, of course, are the current thing that's happening. So a lot of language models use transformers. they have not yet had nearly the breadth of impact just is not compared yet. ConvNets are still the king for now, maybe soon to be dethroned, but they're still sort of the main player for now. So convolutional networks are everywhere. And convolutional networks, the basic idea of these is that instead of having our network structure be fully connected, you use a convolutional architecture to sort of form your activations in your network, right? So you often see networks, deep networks kind of written in a cartoon like this, where you have some input, and then it goes through a matrix to form the next layer, then another matrix form the next layer, followed by a nonlinear function like a ReLU or a sigmoid. You often see this as a kind of a cartoon for deep networks. And the reality is there are no deep networks that actually work like this, at least not in application. They're never like this, right? What they actually do is they use convolutional filters to go from one layer to the next layer. What that means is you have some little filter, which we'll call W, and you slide it across your whole image to produce the next layer. Then you follow it by nonlinearity. That is how deep networks, sort of almost full stop, actually work in practice. Right? And the reason is sort of obvious. I mean, I'm thinking for now mostly in terms of images. This also applies to sound domains, a lot of other things like this. The idea is these things like images have a lot of natural invariances, right? So, an image shifted over 1 pixel is the same image, and convolutions very naturally capture this sort of equivariance that we have in images. They also capture locality, right? You think if you have sort of a set of features at your next layer in your network, you somehow want these features to kind of depend on the nearby features in the previous layer in some very abstract fashion. And convolutions, that's sort of built into convolutions, right? This is sort of naturally the way these things happen. And so this is what really, this is the structure by which all networks really work. Now, the last thing I'll say too is, I should say 2 things to this slide here, is that convolutions as they are used in real networks are all multi-channel convolutions. And what that means is the way you should think of these convolutions acting is that your input is not a collection of just pixel values, scalar values. Actually, each value in input is a vector, right? So each of these are vectors, and your filter is a filter of matrices, right? It's not a filter of individual, just sort of scalar values, it's a filter of matrices, and you get your final sort of product here by sliding your filter of matrices over your vectors to produce another vector field. You will often see that written out kind of in summation formulations because people like to think of convolutions as being sort of one dimension or a single channel, but this is a much more natural way of thinking about it, I think. It's also how it's implemented in practice. The other thing I'll say is if you look at this equation here, is that we in deep learning write convolutions backwards, right? So if you were in signal processing, you'd probably say, well, you have to flip your filter around for it to be a convolution. What you're doing there is a correlation. And I'll just say that, the term correlation is already taken in machine learning. So we couldn't call them correlational networks. So we have to call them convolutional networks. And then flipping them upside down and left, right just seemed too much work. So we don't do it. We call this a convolution. So I get into arguments with my signal processing friends over this, but at some point we've sort of won, right? This is now the dominant use of convolution in papers and such. Okay, so yeah, I think I said this. So these are vectors, these are matrices, and then these are sort of matrix vector products is your operation. All right, so now before I jump into sort of the applications of this, let me just sort of say that what we have all learned in our signal processing courses is that the fast Fourier transform really the FFT command as a way of expressing an image on the basis of the DFT is the best way to implement convolutions, right? It's n log n complexity, n's the number of total points in your image versus n squared complexity if you do it the slow, boring way. But that's only true if the filter size is also O of n, right? So if the filter size is not, if the filter size is constant, then of course it's also constant time to do this sort of the naive fashion of convolution. And even more than that, in deep learning, we typically use really small filters. So the most common filter size is 3. If you actually, I say approximately 3 there, because again, like if the expectation of all filter sizes we use over all deep networks, it's probably a little bit more than 3. I guess not including 1 by 1. So Those are just matrix multiplies, right? But we call them 1-by-1 convolutions for some weird reason. But it's like about 3, maybe like 3.1, amortized over the few networks that use bigger filter sizes than that. So they're basically using size 3, which means that this naive method of just performing the actual multiplications out ends up being faster than using the FFT, than the overhead used for the FFT. But it's actually even worse than that. So the way that convolutions are actually implemented on GPUs is you use an operation called im-to-call, which takes the image and replicates the data multiple times. So it actually replicates the data, the number of filter hit points there are in GPU memory, right? So it copies the GPU memory and then does the whole convolution with one big matrix multiply. And this is, hugely inefficient from any sort of normal perspective. You're actually not just, you're not just doing like the slow operation, but you're also copying memory. You're blowing up your input size. But the fact is that the efficiency of matrix multiplies on GPUs makes this thing just so much faster than other approaches that it's really crazy to do anything else if you want to cram out the last bits of speed possible. So this is sort of, this is in some sense, this is what enables deep learning to be where it is, right? We love things, we love making things go fast on GPUs. In deep learning these days, that is the name of the game. But now I want to talk about sort of, given this, how bad is it to use the FFT? Right, because the story I told before was sort of the typical story of deep learning is that, this is just going to be way faster and everything else is going to be slower. So I think the perspective that most people actually in deep learning would have is that if you actually use the FFT to do convolutions, it'll be 10, 20, 100 times slower. And I'm here to tell you that this is not true. It's actually about 1.5 to 2 times slower to do convolutions with an FFT. It's also not that hard to do because the reality is all these libraries that we use for deep learning have on GPUs, all that kind of stuff, they have very good and well parallelized implementations on the GPU for doing the fast Fourier transform. And they're pretty good. They're not as fast as even for larger filter sizes, they're not quite as fast, but they're pretty good. Yeah, question.
On GPU?
On GPU, yeah. On a GPU, in PyTorch, real libraries, 1 to 2 times, 1.5 times slower, which shocks a lot of people because they sort of think like, oh, this is going to be 10, 20 times slower, right? Nope, it's about as fast. Don't get me wrong, 2 times slower is a big deal if your training process is days, right? It's 2 weeks versus 1 week. But if there's any advantage, this is not that bad, right? If we can capture an advantage of using an FFT-based approach, maybe this has some potential, right? It's also about 20 lines of PyTorch code. So I like having code occasionally. You can't read this, unfortunately, but you can maybe read it online if you're online. But this is all the code you need to implement a convolution in PyTorch. So actually, what the majority of the fun code here is like permuting indices of tensors, because what indices you do an FFT over versus how you batch multiply matrices versus all these things, that takes the most effort. The actual FFT code here is basically you compute an FFT on the where is that? Yeah, you compute a real FFT on the input. You multiply the matrix into FFT space, and then you compute an inverse FFT on to get it back into normal space. And once you've resized this all properly, this works great. As I say, 20 lines of PyTorch, and you can really do cool stuff. So, okay, it's great that it's 1.5 times slower. Like, what is that? It's still 1.5 to 2 times slower. What's the actual advantage? What's a possible advantage to using FFTs to do multiplication and to do convolutions for deep networks? Because they do bring up some issues too, right? So they're like, they're circular. So if you want zero padding, you have to have your zero padding in your nonlinearity or blow up and add zero padding to your image size, all that kind of stuff. It is a little bit more of a pain. It's 20 lines of PyTorch instead of 0 lines of PyTorch because they already have convolutions built in. But there is this really cool capability of convolutions when you use the FFT. And that is that you can invert. I think one of the coolest things about it is that you can invert your convolutions, or you can more generally invert convolutions. We'll talk about like invertibility in a second, but assuming these things are invertible, you can invert them with the FFT. Right, so how does this actually work? I assume probably a lot of people actually know this here, but maybe the CS people that came later don't know this, right? I hear a lot of people registered at the last minute from CS. So maybe you don't know this. I didn't for a long time. You can think of the FFT as a matrix decomposition, right? So think of your convolution, your convolutional operator as just a matrix A, and this matrix is sort of like the matrix form of the convolution applied to ultimately a vector, which would be your image, right? Everything's flattened, but doesn't matter. They're all tensors really, but just think of it as like a matrix applied to a vector. What the FFT does is it decomposes this operator into essentially an orthogonal decomposition. It's like an eigenvalue decomposition of this operator, right? These actually are the eigenvectors and eigenvalues of this operator. Where D here is actually, it's not quite diagonal because we have this matrix vector form of convolutions, but it's a block diagonal matrix. And then these F operators here are the Fourier bases. And so basically what you do is if I want to apply my convolution to this, what I do is I first apply the Fourier transform, that's F times the vector. Then I apply this block diagonal matrix. That's actually for a true diagonal matrix, that's this element-wise multiplication. That's sort of the convolution theorem, right? And then I invert the Fourier transform, which again, I mean, how you do that is not super easy, but the nice thing is that I've lost my code here, but the nice thing is that, even in PyTorch, even in our land of just in deep learning, you have, torch.rFFT, which is the real FFT that you can just do that, and torch.irFFT, which is the inverse operation. So you can do basically multiplication with F and the conjugate of F. Okay, so all that's really easy to do. So now, the very nice thing here is that this immediately lets you form the inverse operation, right? Because the inverse of A is equal to just this thing inverse. And these are unitary matrices, so they are nicely inversions. They are inversions of themselves, and all you have to do is invert this block matrix here. And what this really involves then is the inverse of several block matrices that are n channels by n channels. However many channels you have in your convolutional structure, that's the size of your matrix you're inverting. And the nice thing about this is all really easily parallelizable, right? Because I can invert, it's a whole bunch of matrices that I need to invert, but I can invert them all in parallel. I can, solve all these things over batches of data natively on the GPU using built-in functionality of PyTorch. And because you have to do the inverse sort of once, and then you're done with it, especially at runtime when I'm doing inference, I can just pre-compute those inverses, and then I'm done, right? Then it's actually just as fast, essentially, as doing any other convolution. So very, very sort of nice here. And not just our work, but a whole bunch of papers have actually leveraged this to all sorts of effects in deep networks. Some of these were before our work, some of these were after our work, but I just want to emphasize this is not like, we're not the ones discovering this here. For the first time, people are doing this. You can do things like that. There are these models called normalizing flow models that are a generative model, generating images, things like that. You've probably seen, not this model, but you've seen a different one, but these things that generate like artwork and stuff from a prompt. Those are generative models, and a class of generative model called normalizing flows requires the invertibility of individual layers. And so in order to make this work with convolutional architectures, you need to be able to invert them. And people have used FFT-based convolutions for this. If you want to compute singular values of convolutional layers based for generalization bounds, things like this, you also need to leverage an FFT because you just compute the FFT and then compute the singular values of those block matrices. That's how you compute the singular values of a convolution. And so these things they're somewhat used, not very widely, but a little bit widely. And the thing that I actually want to do here, in the time I have left, is just give sort of a few examples of the things we have done with these tools that have led, in some cases, to sort of nice effects. So one very cool thing you can do with invertible convolutions is you can form orthogonal convolutional operators. So orthogonal operators means that, it retains the norm of the norm of the output, the same as the norm of the input for any input vector. And there's a very easy way to form orthogonal. I mean, forming an orthogonal convolution in general is actually quite hard. Like, how do you parameterize weights of a filter such that your convolution, the total convolution, is orthogonal? It's not actually easy to do. It's quite, there's no actual parameterization in terms of the filter weights themselves that can guarantee orthogonality. What there is, though, is there's this very nice sort of bijection between the set of all skew symmetric, really operators, but matrices, the way I think about it, and orthogonal matrices here, which is called the Cayley transform. So if I have a skew symmetric matrix A, that means A plus A transpose is 0. Then if I form I minus A times I plus A inverse, this matrix Q is always going to be orthogonal. And this is actually a set of all orthogonal matrices with a little hole for ones that have all negative eigenvalues. But it's essentially a set of all, almost a set of all, I should be careful in the math department here, but almost a set of all orthogonal matrices here. And the cool thing is we can do the exact same thing now to parameterize a very rich set of orthogonal, truly orthogonal convolutions, which have all sorts of benefits when it comes to sort of the things like robustness of the networks, how much you see, how much you expect your norms of vectors to blow up, how much influence, how much change inputs can have on outputs, things like that. And the idea is you just do this. You just sort of take, form an orthogonal convolution by doing the Cayley transform, which you can't do natively because I can't invert this normally, but do it in Fourier space, right? So do it after the Fourier basis. You can form this matrix here. This matrix is a bunch of block diagonal matrices. I can invert it explicitly, and I can form through this construct an orthogonal set of convolutions. Furthermore, I always know this is actually always going to be invertible because this matrix here is skew symmetric. So this one's here skew symmetric, and which has all imaginary eigenvalues. So I plus this is always nicely invertible, well conditioned. There's no problems of invertibility, et cetera. That is something you have to deal with if you do orthogonal convolutions. You have to make sure that you're not going to be inverting something that is, in fact, essentially has eigenvalues very close to 0, right? And when you and again, because I like to put up code here about this. This is about 8 lines of code in PyTorch that actually implements this. Once you have that other code, right? So once you have this, all you have to do is sort of an inverse in the middle there, and everything works. And by the way, this is also PyTorch. The beauty of automatic differentiation, right, is that you just do this, and you can also train these networks like this. This is trainable, a normal PyTorch module, just an orthogonal convolution in 10 lines of code. And these things can be very, very nice. This is work that came out in iClear a few years ago. So what are the advantages? Well, when we do things like try to validate robustness of these networks, we can use this to construct networks that are more robust than other ones. Essentially, robustness is about how much input perturbations can change the output of the network. And you might imagine that a very nice way of controlling that is to ensure that your layers are orthogonal. That will ensure that small inputs can't have a big effect on the output. And so, in fact, with these methods, you get a notable boost in certified robustness from these approaches. It's not huge, right? These are actually other orthogonal parameterizations of convolutions, but they are not complete. So these are actually, in some sense, just a better parameterization. The same with empirical robustness. You can look at larger networks, even if you're not certifying their robustness. You also get networks that are just a little bit, and again, a little bit. I'll come back to that in a second. More empirically robust. I was told I only have 25 minutes, and I was planning for 30 minutes, so I'm unfortunately going to have to go through this last one a little bit quickly, because I do want to highlight my main points in the end. But what I'll quickly say is that we've also been working on the class of networks, doing a lot of work actually in my group on a class of networks called deep equilibrium models, which are networks that rather than compute their output through a fixed computational graph, they solve kind of a recurrent problem to find a fixed point to some nonlinear operator. All right, so you have some input x, and rather than sort of just put it through a fixed number of stages in the network, you find some solution to a nonlinear equation where this function f is basically itself kind of just a single layer of a deep network, right? And so it turns out this is actually equivalent in some way to sort of an infinitely deep fixed point network. I won't talk about this. There's a lot of work we've done. The name to search here is deep equilibrium models, or DEX. And there's been a whole lot of work in that. I'll skip over the results. We have actually a lot of good results on these things, including like segmentation and image classification using the same model where we can get essentially state-of-the-art results. And we can do things like segment images. And these are actually, relatively large scale networks that can do this kind of stuff. What I will say for the purposes of this talk, though, is that there's a nice class of these, whenever you have like a fixed point model, one obvious question is, well, does this fixed point actually exist? Is it unique? You can actually find it? And the answer is no in general. You can't always guarantee existence. This is the same, as with most deep learning, you can't guarantee anything. But there is a really beautiful class of networks, essentially based upon that leverage some properties of monotone operators to guarantee for a certain class of fixed point network that looks like this, where you essentially have one nonlinearity, one linear function, and input injection. I can specify conditions which guarantee this will have a unique fixed point. And what they essentially do is they reduce this problem to a monotone operator splitting problem. And so there's certain monotonicity properties or semi-definite properties essentially required on your matrices here, which are actually not that hard to satisfy. You can enforce these things to be satisfied by the parameterization of the network. Now, the point that is important for us here is that solving for this fixed point is made a whole lot faster. If W is a convolution, for example, or even a structured convolution, solving for this fixed point is a whole lot faster if you can actually invert W. Not the whole thing, but the way to think about this is if you're sort of trying to solve a fixed point here, and if you can kind of precondition your solver with the inverse of W, you will do a whole lot better, right? It's not quite preconditioning. It's actually a method called Piesman-Rackford splitting in monotone operators, but it's essentially the same thing. Essentially like a preconditioner on your iterations to solve this fixed point. That can be done a whole lot better if you can invert actually this matrix here. Some identity plus some alpha times W here. Okay, so that's maybe not a huge deal, but the basic premise here is that in certain structures of these networks, you can solve them much faster if you actually can invert convolutions. So we have at least some small scale examples. These are not as good as the examples you see on sort of the non-monotone versions of these things. Monotonicity is a big constraint. But compared to other things like neural ODEs that also have guaranteed fixed points, these work much better. So sort of from a standpoint of the set of implicit models, they're called, that are guaranteed to have a fixed point, these networks work quite a bit better. And if you use methods that don't use inversion, you very often do not converge at all to a solution. Whereas if you use methods that use inversion, you will converge both more rapidly and essentially the same time complexity, because you can just invert it once, do your solve, and the cost of the inversion is actually amortized over the cost of the whole solve. It ends up being almost exactly the same speed as normal convolutions. Okay, so I have a few more minutes now. Let me just give some final thoughts here. So the theme of this talk, if I was to sum it up, and again, this is sort of a talk giving for the first time here, so I'm curious of all your thoughts, to be honest. But if I were to sum up kind of what I'm presenting here, the summary would be, those things look cool, looks cool. I'm glad we can do those sorts of things. Seems like a lot of potential here. But it works great on niche models, on kind of toy problems, basically cases that we don't really care about, right? At least, that Google wouldn't care about, right? Or that large companies wouldn't really care about when I go. I mean, they do, because they're full of sort of mathematicians there too. So they also really like these things. But when we talk about the practical implications of these things, are they having a big effect? No, they're not. No, these are still sort of a curiosity. Where is the impact on the true state of the art in deep learning? And I think actually this is a good question to ask for everyone kind of working in academic research on deep networks, because we all really like math, right? Presumably, if we're here. If you haven't read it before, Rich Sutton, sort of a famous one of the founders of the field of reinforcement learning, has this great article called "The Bitter Lesson," and everyone should read this if you haven't read it before. It's like it takes a 3-minute read or something like that. He sort of goes to describe a big problem with the field of machine learning is that we always are inclined to build in structure into our models because it makes us happy when we build more complex models and we feel good, we feel like we're accomplishing something and they work a little bit better. But these things are always in the long term dominated by methods that just make use of more computation and which scale better, right? And this is not, I mean, this is not and this is historically a common occurrence. And so I don't have an answer to this. And I think it's a fair critique of a lot of the work. You know, a lot of my desire to put in this structure into networks comes, I think, from a belief that this structure should help us, that it's the right structure. It's not based upon actual empirical evidence that it helps us. So I don't know where exactly to go from here. I think there is a legitimate debate to be had here. Is this really the case here? I think there's a fair debate to say, you know, is this, Rich was talking about sort of building in structure about how we think. So a common theme in AI was to try to, you know, build in the logical reasoning and stuff into networks. And so he's sort of railing against that to a certain extent. Even he says that convolution is one structure that actually does work, that has proven very efficient, undeniably, right? So this is one thing. And I think in some sense, there is this difference between building in, you know, how we think versus building in how the world works into our networks, right? So that one, this secondary one seems to be quite actually useful in a lot of cases. When we can build in invariances, this seems legitimately helpful in a lot of cases. There's this famous paper called The Unreasonable Effectiveness of Data that Google released, but of course that was a play on the much earlier paper on the unreasonable effectiveness of mathematics and natural sciences, right? So it really does seem that there is a huge value in building in mathematical structure that we do know about and do believe in into our models. And I guess the ultimate takeaway should just be that I am convinced in the efficacy of the things we can do with FFT-based convolutions over normal convolutions and their applicability and ultimate usefulness in deep networks, precisely because the speed loss is not that much and you gain so much additional capability in your ability to invert them, to take the actual decomposition. All these things are really, really important, I think. And so rather than try to convince you that this is, you know, it's a solved problem and you should all go just use our code, what I actually hope to convince people here is that the code is out there, right? It's in these slides here, but it's also in our papers. These are easy and they're powerful, and you should think about using them in your networks and in your work in deep learning, because I think if I can galvanize the community to be thinking about these things, that's much more effective than trying to sort of do it all in our group and hope that we can find the best ideas. We certainly can't, and I hope I can convince people here to be thinking about this intersection of deep networks and FFT methods for especially for convolutional neural networks. Thanks very much. Yeah. Sorry, was the here? Oh yeah. So Z here is a tensor. Z is like a huge tensor of whatever order you want. So Z, think of the Z as like the set of all hidden units in the network, right? So Z is a big collection of multiple tensors concatenated together. I mean, I think in this example here, Z basically is, sorry, I have to go through things. Z is a concatenation of multiple different hierarchies of the hidden layers of a convolutional network that you solve for simultaneously. And that actually is the case that we use even in the monotone case. We still use that same structure. So Z is a collection of rank 4 tensors in this case. So yes, yeah. Okay. Yeah. Oh yeah, so the solution is parameterized by the parameters of the function f, which are the weights of this like single layer function you have, right? So your function f here is essentially one layer of a neural network. It's one convolution, or really a collection of convolutions in some structured sense. And I probably should have put like F sub W there, because F is parameterized by the weights of your architecture, the same way a normal neural network is parameterized. The difference is that the forward pass involves a fixed point computation instead of just a single forward pass through the network. Yes. So we want to find just 1, 0 for a given W, right? So we want to find, given the current network, the forward pass of the network is defined as finding a fixed point. Now, you will adjust your parameters of your network just like with normal. And this was brief, so I apologize for this part being brief here. It's a whole nother talk to describe these things. You will find the parameters of the network the same way you find normal network parameters. You will train those parameters W to minimize some loss function defined in terms of sort of the output of your network, right? And you will find that actually via gradient descent, computed via implicit differentiation, because you're implicitly differentiating through this fixed point. So at a high level, this actually works the same way as deep networks, but you are just computing in your forward pass. The forward pass involves essentially a solve for a fixed point of some nonlinear function. Yeah. Yeah. Sure.
So what do you think about
Oh. Yeah.
I think some of the models are like easier to learn by the model, but perhaps their experience.
Yeah. So the way I would say it is, the way I would respond to that is I am I'm often suspicious about attempts to explain, especially sort of the broader behavior of deep networks by reduction to simple properties of the input. So if we were able to classify images via simple properties of the input, in some sense, we would not need deep learning to begin with. And this often makes me a bit skeptical of explanations saying, oh, deep networks learn the high frequency things, or they rely on high frequency in order to classify it well. And that is an FFT just of the input itself. My hope here is to use FFTs in the internals, in the guts of the network, not as a way of analyzing the input. Signal processing has done that already really well. And I think there probably is a lot to be learned just sort of using spectral representations to maybe augment networks and things like this. But it's already been done in some way, because we already use JPEG images, right, to feed our networks, right? So I am a bit inherently skeptical about using simple spectral properties of the input to a network to really characterize what goes on inside these very, very complex things. And I guess that, and maybe at a higher level, I also, the more and more I think about it, the more I'm shying away from trying to steer towards interpretability of these networks, because I think it's a really fraught question in a lot of ways. But this is a much bigger topic, but that would be my short response.
One consequence of the continuum is to come up with like orthogonal convolution. Middle you have a
Yeah.
The exponential function of that.
Mm-hmm.
That basically orthogonal.
Oh yeah, so the exponential is another way of doing it, right? So there's two ways you can do this. You can either take the matrix exponential of the skew symmetric, but it's still how do you compute the matrix exponential of a function? You compute the eigenvalue decomposition, and then you exponentiate the individual elements, right? So you have to do it either way. You have to do an FFT for it. So this is one way of doing it. It's a little bit easier, it's a little faster to do a inverse than a matrix exponential, because you like an exponential will require you to do an eigenvalue decomposition of these D matrices here, which is a bit less well conditioned in practice in terms of, actually here it would be fine, but it's just one more thing to do. It's a bit slower than just inverting it for PyTorch, right? So a matrix inverse is 1/3 or 2/3 n cubed, whereas an eigenvalue decomposition is more than that, right? So essentially what it boils down to is to do the exponential of A, you need to compute its eigenvalue decomposition, which is slower than computing the inverse of this thing, constant time. Yeah, but that doesn't actually, doesn't work. That's not truly orthogonal, right? And then then you always have some error terms that like make it very unorthogonal in practice. Yeah. All right.
So let me thank our speaker again. Thank you so much.
Thank you.
Everyone, especially the poster presenters, come back at the quarter past 2 o'clock to find out the winners of the poster. So like
Thank you. Yeah.
On the cloud, right?
On the cloud, yeah.
Very nice, by the way.
Thank you.
I think that